So let's say you have the equation 3 to the power of x is equal to 9. Well, you might be thinking, well, this is pretty easy. X is equal to 2 because 3 squared is equal to 9. You would be right. But the thing is, you only know it because you know that 3 squared is equal to 9. You don't actually know how to do it when you have bigger numbers that you can't just do in this way, right? For example, let's say we had x cubed is equal to 210. You could just cube root everything to get x is equal to the cube root of 210, which is, I don't know, whatever value it is. Let's just do it on the calculator right now, which is 5.94. So x is equal to 5.94. But if we have 3 to the power of x is equal to 210, there's no calculator-like way we can do it to get a surefire answer unless we know somehow what x is, because in this case, x would not be an integer. I'm 99% certain you would not be able to get the value of x without a calculator. The thing is, how do we write this in a way that the calculator can also compute this answer for us? Because right now, we can't put 210 to the root of x or something. We can't do that. We have to write it in a way that the calculator can understand. And that's why we use something called logarithms. And personally, logarithms used to be that thing when I was in like grade 3 where I'd be going on to something like mathletics and I would be like, this is the hardest level possible. But really, logarithms aren't that hard. They are not actually that daunting. You can rewrite this in another form. You can rewrite this as log to the base 3, 210. And essentially, we can extract an equation from this. Let's say we have a to the power of x is equal to b. We can write this in logarithmic form as log a b is equal to x. And in this way, we can actually put it into the calculator and it works. So let's say we had something else. Let's say we had 2 to the power of x is equal to 710. Well, we would write this as log 2 710. And the calculator could do it for us. But the problem with this is that the calculator cannot do it to bases other than 10. So the normal logarithm is just to the base 10. So it doesn't actually say log base 10 and then it says the number. It just says log. So we have to find a way to convert it in such a way so that the calculator can also understand it. So taking our example of log to the base 710, well, the green calculator I'm talking about in this case, which is what you get for the add math test, which won't allow you to do it like this, we have to convert it into a way that's to the base 10, because that's the only thing the green calculator can understand. Well, how do we do that? We use something called the change of base rule, which means we can write something like log AB as log CB over log CA, where C is any base that you want it to be. And in this case, we can make C 10 so that we can make this log B over log A. So theoretically speaking, if we had log 710, where A is 2 and B is 710, we could write this as log 710 divided by log 2. And when we put this into our calculator, just give me a second while I do that, over log 2. That gives us 9.47. And we can see this works because if we write this back in its indices form, which would be 2 to the power of x is equal to 710, and we input 9.47 as x, 2 to the power of 9.47, it gives us a really close answer because 9.47 is only to two decimal places. In this case, it would actually be 709.18. So we're only a bit off. If you ran it to more decimal places, it would have been more exact. So that's called the change of base rule, and we use this formula right here. Now, there are a couple of rules we should first know about logarithms. I kind of jumped the gun a bit with the change of base rule, but it's all right because we can still come back to this. So, rule number 1. With logarithms, if you have a different base, let's say you have log 2x and log 2y, let's say they're added together. Not log 2, sorry, that defeats the point of what I was going to say. Log 3y, you cannot collect them together because there are different bases. It's a bit like, let's say you wanted to add x and y. They're going to have to remain this way, right? Because they do not have a like term, so you have to collect like terms. It's a bit algebraic in that sense. Okay, and rule number 2. When you have something with a common base, like log 2x plus log 2y, that's equal to log 2xy. You multiply the thing in this position over here. The bases remain the same. And then rule number 3 is that log 2x minus log 2y is equal to log 2x over y. So this over here, again, are the only these things over here are the only things being affected. And this almost acts as a division sign between these things, and this acts as a multiplication sign. Yeah, logarithms work a little bit differently in that sense. Rule number 4. If something is written like log 2x squared, you can bring this to make it log 2x. Moving this here can work, and vice versa as well. So those are some main rules with logarithms. The first thing I would also encourage is you change the thing in here to an appropriate power that represents this. For example, if you have log 4, if you want to evaluate this without a calculator, you can rewrite this as log 2 squared, which can be rewritten as 2 log 2. And when a and b are the same, when log a, b, and a and b are the same, that means it's just equal to 1. So this is 2 times 1, which is equal to 2. So our answer for log 4 is equal to 2. And that makes sense because if you rewrite this in exponent form, it's 2 to the power of x is equal to 4. So in this case, x would equal 2. So what I mean by this is try and equate the base with the actual number so that you can easily evaluate it. But that's only true if they're direct powers of each other, if they're integers, if x is an integer. But if it's not, then you'll have to do it with the calculator. So let's try something like this. So let's write these as a logarithmic equation in base 10. So that means, of course, that you don't have to write log to the base. You don't have to actually write, let's write it here, log 10x. You can just write it as log x. But let's look at these equations here. So d is equal to 100 over n squared. Well, what you do to one side can be done to the other. So you can write this as log d is equal to log, and then in brackets 100 over n squared. Now, using what we know about logarithms, this can be written as log d is equal to, and then we can use the subtraction rule because there's a divide sign in here. So log 100 minus log n squared. And we can simplify this because we can bring this down over here, and we can evaluate this. Log d is equal to, and then here we have log 100. So realize that since it's to the base 10 to the power of x can get us 100 with an integer. 10 squared gives us 100. So that means log 100 is actually just 2. So it's 2 minus, and then we can bring this down here to give 2 log n. So this is the equation here that we got in. That's correct. Now let's go to question B. Wait, let me just write this as question A. So g squared is equal to c cubed d. Well, we can obviously do the same thing like we did last time and give log g squared is equal to log, and then brackets c cubed d. And notice again that they've used another rule. They've used the addition rule this time. So Oh, and additionally, you can write this power here. So it can become 2 log g is equal to, and then we can use the addition rule, which is log c cubed plus log d. And then we can obviously bring this down as well to give 2 log g is equal to 3 log c. Oops, I wrote this capital. You shouldn't. Plus log d. And that's correct. Oh, and I have to mention a couple of things as well. So, in general, when you see a question that has lg instead of log, realize that they're actually the same thing. Because my math teacher told me that apparently just people were too lazy to write the extra O. I prefer to just write log, but you might see log instead. Another thing is that you might see, especially in add math, you might see ln. And ln is actually the same thing as log to the base e. So if you see ln x, it's log to the base e x. And e is essentially just a number that's equal to 2.71 something something. It's just, I don't actually know what the significance of e is or why we use it so much in math, but just know that it's log to the base e. It's called a natural logarithm, in other words. So for our final question, let's evaluate these two parts. So we have log 927 as our first part. Well, we can use two methods. We can either use the change of base rule, or we can use our understanding of logarithms, which would be more effective without the calculator. So let's say this is a calculator paper. We can just use change of base rule. So let's set our base to 10 and then rewrite this as log 27 over log 9. Because remember, this part always goes in the denominator and this part always goes in the numerator, which would give us, let me just put it into my calculator, log 27 divided by log 9. It just gives us 3 over 2, which is equal to 1.5. And that was a very easy way of doing it. But what if we don't have a calculator? Well, let's just write this again. So we have log 927. Well, we can understand that 27 is related to 9 due to being 1.5, clearly. But we can also just rewrite these both as separate, like as things that like both of them are like drawn together by a specific number, but we have to rewrite them that way. So what I mean by this is that 9 is equal to 3 squared, while 27 is equal to 3 cubed. So we can rewrite this. We can rewrite this as log 9 3 cubed, which would be easier, which is equal to 3 log 9 3. And then we also should remember here, this is also like possible to evaluate, because log 9 3 is essentially the same as 9 to the power of x is equal to 3. And we know that the root of 9 is equal to 3. So 9 to the power of half is equal to 3. So x is equal to half in this case. But we're not done here. So it's 3 times a half, which is equal to 3 over 2, which is equal to 1.5 once more. So we got the same answer. While I did say that 9 equals 3 squared, it's not necessary to change the base, because that just makes it a bit more complicated in my opinion. I prefer to just change this, because then you can manipulate the power and bring it to the front, and then evaluate this other logarithm that you're left with easily. Now let's look at this next problem. Let's do it both ways again. So of course we can do it the first way, which just gives us log 2 root 2. Oh, sorry, nope, log 1 over 2 root 2. Over log 4, which is equal to, let's just do it on the calculator, log 1 over 2 root 2 over log 4. That gives us negative 3 over 4, which is equal to negative 0.75. Now let's do it the other way with no calculator. Well, the first thing we have to realize is 1 over 2 root 2 takes some manipulating. So let's first just isolate this and try and figure out how do we actually write it as an easier number to understand. Well, first of all, let's just make it a single number. Let's raise it to a power. So it'll become 2 root 2 to the power of -1, because we're gonna flip the fraction around and get rid of the numerator as 1 and make it 2 root 2. Well, 2 root 2, we can also realize, can be written as 2 to the power of 3 over 2, because 2 to the power of 3 over 2 is just the same as this, which is equal to 2 root 2. So we can now write this as 2 to the power of -3 over 2, because we already have this negative sign over here. So this is equal to this. Now we have that, we can write this as log 4 to the power, log to the base 4, 2 to the power of -3 over 2. And we can draw this to this side, the power, to make it -3 over 2 log 4, 2. And what's great is this is actually very easy to generate, because we can rewrite this as 4 to the power of x is equal to 2. And we know that the root of 4 is equal to 2. So x also has to be a half, like we had in the last case. Now we have that, we can say that -3 over 2 times half, because we've replaced this with half, will give us -3 over 4, or the same answer as last time. So you can see that this is a non-calc way, and this is a calc method. And both of them are very helpful. If you have a calculator, definitely go with the above method, because it's also foolproof and it's also a very efficient method. But if you don't have a calculator, fear not. You've got this method and this method, which are both very helpful. And especially if you can tackle something like this, which is quite a complicated logarithm, you should be fine for basic logarithmic equations. In the next video, we'll go over another thing called U substitution in logarithm. That's also very helpful when you get more unfamiliar problems. That's more of an math concept, but it's still worth also reviewing in CIM. And then after that, we'll go over some basic logarithmic problems. But for now, that's it for this video. Thanks so much for watching.